That's where we'll focus here and get this up and record here for a little bit. All right, so on the board here, I've got a little bit of a synopsis of the things that we talked about on Friday. We learned about this thing called the derivative, and that's f prime. That mark right there means f prime. So f of x is our original function, our amount function. Those are different ways to talk about a function that, in that way. And then f prime is connected to that f function, but what it means then is the rate of change of the f function or the slopes of the f function. Either of those are interchangeable. It depends on what you're doing in that problem, which will be to your advantage to talk about. Okay? Now, a couple of things I want to get from you here. When I write out f of 1 equals 2, what comes to mind? What's that mean? Point on the graph. If you plug in, or what some people say, when you plug a 1 in for x, you get out a 2. But that only really applies if you have an equation somewhere to plug the x. But what it means is there's, on the f graph, you have the point 1, 2. Absolutely. That's what I would hope you would think of when you see f of 1 equals 2. Now, the new thing then, and of course that's something that we did on the earlier quiz that we took, and we hopefully will get probably look at those tomorrow. You know, we're going to be doing section 4. We're doing section 4 today. We're talking about section 5. Section 6 takes several days. Section 7, and then our next quiz, which is probably scheduled for about next Wednesday, probably somewhere in there. Okay. 6 and 7 are the most important ideas of what will be on that quiz. But if you don't understand what's in section 4 and 5, then you're not going to get the stuff in 6 and 7. In other words, 4 and 5 are kind of the foundational things about derivative and slope and what this means and what f prime means, and then we get in 6 and 7 to really using this idea of derivative and f prime and f double prime and so forth. Okay, and then that's where the real meat of the chapter is, and that's what will be a lot on the quiz. But you really have to understand these concepts going forward, just like the stuff in section 2 and 3 and 1 where we learned about function notation, or we reviewed function notation. You got to understand that. All right. So what about when you see f prime of 1 equals 2? What does that mean to you now? Say it.
The slope of f1 is 2.
The slope
of f graph.
The slope of f at 1, right? The slope of the f graph, absolutely. The slope of the f graph when x is 1 is 2. The slope of the f graph at 1 is 2. Or the rate of change of the f graph at 1 is 2. Perfect. But also, and this is probably the thing I really want to make sure we understand today, this, f prime of 1 equals 2, also could mean the same thing you just said up here. What did you say this made you think of? A point on the f graph, right? What could this mean? A point on the f prime graph. Absolutely. F prime is a function itself. It's got its own points and y values. And so this is not only, so this has a double meaning. This means the slope of the f graph at 1 is 2. It also means a point on the f prime graph is the point 1, 2. All right, very, very important that we understand it. And that was good. That was, a lot of people sound like you had that thought out. So, let's talk about number 25. Okay? Number 25, they tell you h of 0 equals 0. And they tell you h prime of x, what do they say? Less than or equal to negative 2. And they tell you that x has to be greater than or equal to 0. So the first thing I would want to do, like you guys just told me, what does h of 0 equals 0 make you think? Point on the h graph. So I'm going to draw the h graph. Now, I don't need the over there because they told me x is positive. So this is the h graph, and it goes through the point 0, 0. Okay, put this up, make sure we're getting working good. Oops. All right. So, all right. So now, what's that? What's this thing tell us? Slope is less than 2. Now, here's with negative numbers and less than greater than, we got to really be careful. What does that mean, slope is less than negative 2? What are some slopes that would be less than or equal to negative 2? Negative 2, negative 3, negative 4. This is what we're talking about, right? Now, here's where it gets a little tricky. Negative 2, negative 3, negative 4, negative 5. Those are slopes that are less than negative 2. But the graph that has a slope of negative 3, negative 4, negative 5 is getting what? If the slope is going negative 2, negative 3, negative 4, negative 5, what's happening to it? Steeper, right? So in a sense, we almost think the slopes are bigger, but the numbers themselves are actually littler. You get what I'm saying? So there's really, you've got to be careful with increasing, decreasing, little and big when we're talking about negatives, okay? So we're talking about slopes that can be negative 2, negative 3, negative 4, and so forth. All right, so then they ask us this question about h of 5. Well, okay, h of 5. Just talk rise over run. If the slopes have to be negative 2 or negative 3, numbers like that, if we go over 5, what do we know we got to do? We go down how much? Well, if the slope is negative 2, every time we go over 1, we got to go down 2. Over 1, down 2. Over 1, down 2. So if I go over 5, I got to go down 10, but maybe more, right? Because the slope could be negative 3. So I might go over 5 and down 15, right? But what do we know? We do know that h of 5, that's the y value at 5, has to be below negative 10, which wouldn't that be less than or equal to negative 10? That'd be below negative 10. Now, it said to explain. I think a picture with kind of a slope triangle and then a few words about that would be a good way to explain that. You say, hey, the slope is less than or equal to negative 2, so if you go over 5, you have to go down at least 10, but maybe more. And then, so the next question is very much the same. It says, okay, h of 3 is less than or equal to 5. Well, geez, if you go over 3, could you go up 5? If you go over 3, could you go up 5 in this case? No, if you go over 3, you got to go where? Down how much? You got to go down at least 6, right? You're down here at least negative 6. So, are you going to be below 5? Yeah, for sure. Is h of 3 going to be less than or equal to 5? Absolutely. It's going to be way below. As a matter of fact, it'd have to be below negative 6. But it definitely will be below 5. Yeah.
Why does it say less than equal to 5?
Well, again, it's or. It could be either or. So yeah, that's a great question. I'm glad you said it because a lot of people might be thinking. So I'm saying to you, is it true that h of 3 is less than or equal to 5? And what you're saying is, it almost feels like that statement's false because it can never equal 5. Right? If I say it's less than or equal to 5, does that mean it has to be both? It has to be 5 and also then possibly less than? No. Right now, is it a true statement that I have $1 million or less in my pocket? It's a true statement. And I don't have $1 million, you know what I mean? Even though it's impossible for me to have $1 million in my pocket right now, it's still a true statement to say I have less than or equal to $1 million in my pocket. Okay? Because of that or. It could be one or the other. You're right. It's unnecessary to have it there. It's unnecessary. In this one, you would have to have less than or equal to, right? Because it could be negative 10. In this one, there's no way h of 3 can be 5. That's what you're saying. There's no way h of 3 can be 5. But it's okay to say it's less than or equal to 5. It's okay to say it's less than or equal to 5. Okay? All right, now they say car talk. So what that is saying is right here where I said f prime could mean slopes, but f prime could also mean rate. So let's think of a rate, like miles per hour. So let's pretend this was miles an hour. Let's pretend the h graph was miles, and the x is hours. So h prime is miles per hour, right? So what would this statement be saying? H of 0 equals 0.
Arc of 0 miles, 0 hours.
So that's my starting point, right? So let's make this 0, and we'll use that east-west thing. So east is going to be positive, right? Think of this as a number line. So positive numbers going this way, negative numbers going this way. So, okay, here's 0 right here. So I'm starting at 0. And then what's this saying? This is my speed, right? This is my miles per hour. Now, speed and velocity are two different things. You guys in physics know that, right? So this is my velocity, technically, not speed. My velocity, let's do miles per hour. So 2 miles per hour. But what's the negative mean on velocity? No. It doesn't mean you're down. It's the direction you're going. So a negative would be what direction? West. So this is saying I'm starting here at the origin, and I'm going to go 2 miles per hour west, or it's less than -2, so it could be -3. So what would that mean? 3 miles per hour west, or it could be -4. 4 miles per hour west, but I'm going at least 2 miles per hour west. It could be going faster, right? 3 would be faster, 4 would be faster, okay? But it's still west. So then what this would be saying is what?
In 5 hours.
In 5 hours,
You'll go at least 10 miles west.
you're at least 10 miles west. That's what this is saying. So if I start here, and I head west at 2 miles an hour or more, faster, then after 5 hours, I'll be at least 10 miles west. That makes sense. Okay? But I could be farther west. The less than means even farther. This less than means even farther west, right? -10, but I could be less than that. I could be -15, -20, right? So I could be even farther west. So I'll be 10 west or farther west. Okay, what's this one mean? This is kind of a tricky one. What's the 5 mean? I'll be west of
5 miles.
5 miles east, right? If I go 2 miles an hour west, then in 3 hours, I'll be west of or at 5 miles east. Well, I won't be at, like we were talking about with John a minute ago, but I will definitely be west of 5 miles east, right? I'll be west of 5 miles east. That's car talk. I mean, that's using it as a rate. Okay? And yeah, definitely be west of 5 miles east. I'll actually be west of 6 miles west, right? Could be 6 miles west or west of that. That's the speed limit law. That's a thing we did at the end of the period yesterday. Just says if you know how fast you're going, you know how far you've went. All right, let's talk about 41. Okay. 41 says that H is the hours between sunrise and sunset, which means hours of daylight. And they want you to describe this. And I told you the other day that you will definitely have one of these on the next quiz where I give you the context of a function and its units, and I ask you these types of questions about it. Now, what I would do to help in this, whenever you have units, I think it's helpful to make a graph. Let's do a graph of H, and they didn't really tell us. I think T is the input, I think. Didn't they say that? Okay, so what's T in?
Days after
Days after January 1. Right? That's T. What's the units on H? Hours what? So wouldn't that be hours of daylight? Would that be a good way to say it? Let's call that hours of daylight. We got hours, we got days. Hours of daylight and then days after January 1st. That's H. So, what would be the units of H prime? I mean, yeah, it's about fast, but isn't it? Just give me the units. Isn't it just the y units divided by the x units, right? That's what we've been talking about. Miles, miles per hour, that kind of stuff. So it's hours of daylight per day after January, per day, right? Per day. Hours of daylight per day. That's what H prime is. Hours of daylight per day. So that's this number right here, the 0.05. So somebody want to take a crack at this? Yeah.
100 days after January 1st, the hours of daylight are increasing by
0.05 hours. We don't really talk like 0.05 hours, so take that times 60, I think it's 3.
Yeah.
0.05 would be 3 minutes. 0.05 hours, take that times 60 minutes in an hour. Would be 3 minutes. So you could say 0.05 hours per day, right? 100 days after January 1st, the hours of daylight are increasing. Now, why did you say increasing?
Because it's positive.
Because that's positive. It's a positive number. If it was negative, we just said decreasing, okay? Hours of daylight, 100 days after January 1st, are increasing 3 minutes per day. That's what that would be a great way to say it. A better way to say it would be on the 100th day. Let's be specific. And an even better way to say it would be to calculate what the 100th day is after January 1st. Now, I wouldn't get that picky, but let's see. January has about 30, February has not quite 30, March. That's 3 months. That'd be about 90 days. So what about April 10th? Roughly, give or take. On April 10th, here'd be a great way to say this. On April 10th, the hours of daylight are increasing 3 minutes per day. Even better would be to say on April 10th, there's 3 more minutes of daylight than on April 9th, the day before. Now, think about that. In April, are we gaining minutes of daylight in April? What's the shortest day? The shortest day would be the winter solstice, December 21st, which this year, the other class reminded me, is also the end of the world, right? On the Mayan calendar thing, right? Which also happens to be the end of the term, our last day of school, which also reminds, I mean, so, last day of the term, so if the world's going to end, what the heck, I mean, not that day. But that's also the end of the term. That's also our one, maybe only extra credit opportunity this term. Calculus carols.
What?
Calculus carols. You, for some extra credit, now it's not enough extra credit to take your grade from like a C to an A or anything like that. But for a few points extra credit, if you want to take a calculus carol or a calculus poem, like it was The Night Before Christmas or something like that, and rewrite it using calculus terms and things about this class or whatever, and perform it in front of the class. You can do it in a group with a partner or solo. A few more bonus points if you do it solo. If you want to bring in an accompaniment, and then people play the guitar or bring in somebody that whatever, that's fine. You want to dress in costume, that's fine too. And it will be recorded for future classes to see. Okay? And I've been recording it for like 15 years, so at some point as we get close to there, we'll watch some of last year's and other year's classes if you want. Some of your brothers and sisters, if they've been in class, we can pull those out and look at those too. But anyway, so I digress. But that's coming up the last day of the term. So December 21st. But December 21st is the shortest day of the year. So after December 21st, the days start getting long. So in April, we're gaining minutes of daylight. And then the shortest or the longest is summer solstice, which is roughly June 21st, right? And so we're gaining minutes of daylight until then, and then we start losing. So right now, we'd be losing. So right now, this would be negative. Actually, we're answering part B now, aren't we? Part B says, when is H prime less than 0? So when is H prime negative? Well, that'd be between the summer solstice and the winter solstice. Now, what values of T is that? Well, you'd have to figure out what day June 21st is. 170 days or somewhere roughly, 175, somewhere in there. So somewhere between there and December 21st, which would be, 10 days short of the end of the year, so 355. So somewhere between 175 and 350 or something like that, roughly. Okay? So between the summer solstice and the winter solstice, H prime would be negative, because then you're losing minutes of daylight. Okay? Something I always find kind of interesting, too, is if you, this puts it in kind of a calculus term. If you think about minutes of daylight, if you think about the sun moving in the sky, I'm not talking from east to west. The sun comes up each day, starts in the east, comes overhead and goes to the west. But in the summer, the sun's up higher, right? Almost overhead, right? That days are longer, right? Because of the tilt of the earth and all that stuff, right? So sun comes up in the east, and in the summer, it pretty much comes straight overhead. So if you were to look at a graph of that, looking east, coming west, the sun might be, say, at this point overhead, right? This would be north, the northern sky, this would be the southern sky, right? And so here's north over here, here's south over here, and here comes the sun, right? Pretty much overhead. But this time of year, where is it? In the sky. It's a little more to the south, isn't it? So the sun comes up in the morning, and it kind of goes across more in the southern sky, right? And it doesn't get up as high, and therefore not as many hours a day. Again, because we're tilted tilted away, right? So in the winter, on the shortest day of the year, the sun is almost like down here somewhere. Now, between the summer solstice and the winter solstice, each day, the sun is getting a little bit more towards the south, right? Each day when it comes up, if you looked at its highest point, each day it's just a little bit farther to the south until it gets to the winter solstice, and then it starts coming back more up high, right? You understand what I'm talking about there? Okay, so now when you're at the summer solstice, so you're June 21st, and let's say it gets dark at like 9 o'clock. From the end of June into July, do you really notice the days getting shorter? You don't really, do you? It's because the sun's not moving to the south very much. I mean, each day. It's barely moving. I mean, it's pretty much the same. So into July, even the beginning of August, you really don't notice the days getting shorter. But then you get into school, right? And you get into late August, you get through September. Now you get where we're at right now. Well, I guess it's going pretty fast, isn't it? Especially, of course, after daylight saving time, not get back an hour. But all of a sudden, you notice it picking up speed, right? Till right about there, probably, which would be, what, the equinox, September 21st? Right there in the middle. Now we're on our way towards December 21st. Now the days are pretty short. I mean, geez, last night it was, what, 5 o'clock, and it was over 5, you know, it seemed like it was getting dark already. It's kind of crazy. So, but now, between now and December into January, do you notice a lot of difference in how short the days are? They seem about the same, 5:15, whatever, it's getting dark about that same time. That's because it's starting to slow down again as we come this way, right? Now, you hit December 21st, and then now the days start getting longer again, but you don't really notice it in January, really in February. Then you start getting into the spring, start getting into March, and all of a sudden the days start getting a little longer, and all of a sudden, seeing through here, it's moving faster. It's moving faster. And then you get into May, and then you don't notice it as much. It's starting to slow down. You see how that's working? So if you had to graph that, wouldn't that be a graph? Would that graph kind of look like that a little bit? Well, yeah. Wouldn't it be this kind of a motion here? The days are getting shorter, and at the beginning they don't get short by very much, right? They're getting shorter, but not much. They're pretty flat. But then they kind of go like crazy, and then you get to September, and man, the days are really getting short. But then now that they're getting pretty short, now you don't notice it so much until December. Well, what's that point right there at the equinox? The inflection point. Absolutely. The spring equinox and the fall equinox are like the inflection point. What are the solstices? Local max and min. Not only that, but the name solstice. Sol for sun. Solstice means when the sun stands still. If you think about it, when I move this direction and then I turn around and go the other direction, what do I have to do before I can turn around and go the other direction? I have to stop. I have to stand still. So at the summer solstice, or the winter solstice, the summer solstice, when the sun stands still, in other words, in the northern or the southern sky and so forth. And then equinox, I think, is for equal hours, right? Equal hours a day and daylight and nighttime is what happens basically at the equinox, roughly. But anyway, so that kind of plays into this rate idea that we were talking about, derivative and so forth. So that's I just think that's a cool example, especially this time of year, to think about an example of rate of change and so forth. Okay? All right, now let's 35 and 37. These are really critical for as we go forward as well, these graphs. And so, understanding the notation, the speed limit law, understanding this notation, key parts of section 1.4, understanding this idea of derivative. Now let's look at number 37. Now you're supposed to draw a position, a velocity, and an acceleration graph. Now, we'll talk a lot about this as the year goes on. We will use these examples. Position, velocity, and acceleration. They're just really good examples of rates of change. Now, with our new notation, we know that V, another name for V is what? P prime. And another name for A is V prime, but also V double prime, because it's the derivative of P prime, which would be P double prime. And it's the derivative of V, which would be V prime. Now, if the units on this are miles, and the X units are hours, what are the Y units here?
Miles per hour.
Miles per hour. And of course, the X units never change, so they're always hours. And here?
Miles per hour.
Miles per hour, or miles per hour squared, or miles per hour. So it's always the Y units divided by the X units. Okay. Now, being able to graph a derivative graph is a big part of what we're going to be about today in section 1.5, and also then we go forward into these later sections. I'll be able to compare the two graphs. So what's 37 say? At the origin and steadily increasing its speed. So let's start, it doesn't say where it starts, right of the origin, left of the origin, right? It doesn't say that, right?
Well, after the right is positive, they said it's positive side of the x-axis.
Oh, did they say x is always 0?
Positive,
Well,
yeah.
Yeah, but remember, listen, my x-axis is hours. In other words, we're not going to go into negative hours.
Isn't it the object can only move along the positive axis?
Yes, right. So it's only positive hours, but it can have a negative position or a positive position. So again, think of this as a number line here. So I got negative numbers here, positive numbers here, right? Okay, so it doesn't say where I start. It just says the object moves towards the origin at a steadily increasing speed. So I'm going to start over here at -5, okay, west of Bismarck. And I'm going to move back towards the origin at a steadily increasing speed. So faster and faster. So let's say I'm stopped to start with, okay? So I have no speed. Now I'm coming in here, I'm going 1 mile an hour, then 2 mile an hour, then 3 mile an hour, right? Faster and faster. That's just back towards the origin. It doesn't say I go past the origin, so we won't go past the origin. So tell me, in that scenario, where would I start this graph? Where would my y-intercept be?
Wait, I thought you just said -5. You said -5.
So where did I say I started over here?
You started at negative.
My position is -5. So where do I graph that on the position graph?
X negative hours.
It'll be right there. At 0 hours, right, that's my start. At 0 hours, I'm going to start with a position of -5. So that'd be the point 0, -5. Okay? I see some looks of confusion. Okay? If I just started over here, where would I have plotted that point? Then it would have been positive. Okay? Position can be negative, east and west, right? Left and right. Okay, I'm starting down here. Now, I could have started over here. It didn't say, it just said back towards the origin. Okay, so I'm coming back towards the origin. So now I'm going to the right. 1 mile an hour, 2 mile an hour, 3 mile an hour. Okay, what's this graph got to do? It's got to go up, and it's got to curve up. It's got to be concave up. No, it couldn't be concave. Not if I started down here. If I start down here, it's got to go like that, right? Now, you know what? It'd be worthwhile having another set of axes right down here, because let's just do both at the same time. What if I just started over here at 5? Then I would have plotted it up here, right? Now I'm going to come back towards the origin, but what's my velocity now? If I'm going left, physics people, wouldn't my velocity be negative? Going back this way to the left? Okay, but anyway, this graph, wouldn't this have to come down like that? Right? So it'd be concave down in that case, right? Everybody understands that's concave down? This is concave up, this is concave down. But steadily increasing means getting steeper. They have to get steeper. So they both get steeper. I come back towards the origin. Okay, let's look at the top one first. So now we're going to do the velocity graph. So what's my velocity on this first one? Which direction am I moving? 0 miles per hour. Now I'm going 1. Is that a positive 1 or a negative 1? Because I'm going to the right. And then a positive 2, then a positive 3, then a positive 4, right? But I started at what velocity? 0. So where should my graph start?
0.
Right there. My graph should start there. And then it should go what?
No, because it should be a linear line.
Okay, first of all, let's forget about curved or line right now. What direction should I go right now? Should I go up here or should I come down here? I got to go up, right? Because what did we just say? We said our velocity is going to be 1, then 2, then 3. So that means my y values over here have to be 1, then 2, then 3. Now the question is, should it be a line or should it curve? It's a line because of the word steadily. The steadily increasing came here. Okay? Steadily increasing speed. But what that means is I was going 1, then 2 mile an hour, then 3 mile an hour, then 4 mile an hour at a constant rate of increase. So therefore, when I draw this one, it has to be a line. It cannot be curved because it says steadily. So here my velocity is steadily increasing. There it is. You can see it steadily increasing. But steadily means it's on.
And doesn't the graph look like that no matter where you start? Even if you
No.
start
Let's do this one. Let's do this one. If I start over here at 0 miles per hour, no, it still started. Okay, I'm 0 miles per hour, but now what's my speed? Velocity, sorry, not speed. -1. Now I'm going faster. Now it's -2. Now it's -3. So where would that be? That would have been that one. So what you drew as your original graph is going to determine what your derivative graph looks like. Now I'd like to change gears here for a second and quit talking about velocity. Physics people have a little bit of an advantage there. I want to talk about slopes. This is really key. This graph, if there's one thing you get out of all we do today, it should be this. That the derivative graph here, the y values here are the slopes of this graph. If you get one thing from this, you understand that f prime are the slopes of f. So these graphs here, the y values, are the slopes of these graphs. And if you do that, it makes drawing these graphs really easy. Look at this. What's the slope right here? 0. What's the slope right there? Just make up a reasonable number. 1/2. Well, I like fractions too, but let's call it 1. Right? Make it easy. What's the slope there? Right? Aren't the slopes positive? Now here's where we got to really be careful with the word increasing. Those slopes are positive and getting higher. More positive, right? Higher. That's true. That's increasing. So 1, 2, 3, 4, that's increasing, right? But what else is increasing? -4, -3, -2, -1. Isn't that also increasing? So the numbers themselves, but if these were velocities, what are you doing here? You're actually getting slower, aren't you? So it's really hard. Here the speeds are decreasing, but the numbers themselves are increasing. See, so you talk about a velocity. Here your velocity would be decreasing, right? Your velocity is decreasing, but the numbers themselves are increasing, and that gets really confusing. So what I will say often is the numbers are negative and getting less negative. So there's two ways to increase. Numbers can be negative and get less negative. That's an increase. Or positive and more positive. Okay, I lost money, but I'm losing less money. That's a positive. That's an increase, right? I'm losing money, but now I'm losing less money. So that's an increase. Or I can gain money and gain more money. Okay, and then of course the reverse is true for decrease. So let's look at these slopes. 0 slope, 1 slope, 2 slope, 3 slope, 0, 1, 2, 3, right? Look at these slopes. They start out 0, but then what? -1, -2, -3, -4. That's why the graph goes where it goes. Okay? Well, now that makes acceleration much easier. This graph is, the y values here are the slopes of this. What's the slope of this? Yeah, I'd call it 1. The slope here is 1 throughout. So here the y value is 1 throughout. Got to be a horizontal line. Got to be a horizontal line. Now, what if it would have been this one? Then it would have been down here for the acceleration. Okay? All right. Really key that we can do that. But I think if you think about it as slopes, it makes it so much easier. Okay, now let's back up and do 35. Now, what was hard about 35 is you had so many different possibilities. Well, actually, you had different possibilities on this one, too.
It's still on that screen.
Oh, I used the wrong eraser. Okay, that's always kind of fun. How do we do it? This is good. Eraser's too fat. All right. Yeah. Okay, thank you. All right, so now, let's talk about 35. 35 says the object moves right then left. It didn't say steadily, doesn't say how fast, it didn't say anything. So we got all kinds of possibilities. So it moves right then left. So what did you guys draw? Like a teepee? Now where did it start? We don't even know where it started, right? You could assume 0 if you want. What the heck? We'll zoom 0. So it could have done that, right? Now, to be honest, it's pretty, well, okay. So it could have done that. So let's go with that. So what would the derivative of that look like? Now remember, the y values here are the slopes over here. So what's the slope right there? Say it's 1 the whole time. The whole time, right? Until that peak anyway. Then what? Well, now, this is something that we will talk about. Well, we may not get to talk too much about it. We'll just talk about it right now. We'll probably have to talk about it more tomorrow. But the slope here at this sharp point is undefined. It's not 0. That is not a 0 slope. On a smooth curve like a local max, that's a 0 slope. Sharp point like that, the slope is undefined. Okay? Because it's a sudden change. Look what happens. The slope is 1, 1, 1, 1, 1, and then it becomes what? Negative 1. So how do I draw? Yeah. Well, technically what should happen is that right there. It's undefined at that point, and there's this jump. Now, physically, it would be almost impossible for something to do this. You couldn't be going right at a constant 1 mile an hour, and then all of a sudden turn back and be going left at a constant 1 mile an hour without stopping, slowing down, or something. So it would almost be impossible to do it. Okay? But let's keep going. So what would this graph look like? What's the slope here? 0, 0, 0, 0, 0, 0, 0, 0. Just be a horizontal line right there at 0. The y value would be 0. Okay? But a more realistic picture of this might be what? More of a kind of a parabola shape, right? It's going right, slows down, gets as far right as it can, now it comes back to the left. Okay, if that was the case, then what would this do? Okay, well, what are the slopes doing? Maybe a slope of 4, 3, 2, 1, 0. So would it start up here? And it would come down. Now the question is, would it come down in a line or in a curve? Kind of a trick question. We don't know. They didn't tell us. They didn't say steadily. They just said it goes right, then it goes left. We don't know. If this was steadily increasing to the right and then back to the left, then it'd be a line. Let's do that one first because that's easy. So it would just come down to here. Wouldn't that be the peak? And then it would just keep going. Because it would be going, because you'd be going positive slope, beginning less positive. And that's what this line does. It starts at the y values. Start out positive and get less positive. Then right here at the peak, the slopes go negative. And they get more negative, right? -1, -2, -3, -4, they get more negative. And so this line is negative and goes more negative, right? It's decreasing the whole time. Positive and less positive, negative and more negative. Hopefully, over the course of this chapter, you will look at a graph like this and you'll say, yeah, it's decreasing, but you'll also say it's positive here and then it's negative here. You'll look at, it's important that it was above the x-axis for a while and now it's below the x-axis because that's a turnaround. Okay? What would this be then? Horizontal line. Since it's at some negative value down here, whatever it is. Yes, ma'am. Now, just a quick comment. If this would have been curved, if we would have done something more like that, that would have been okay too, right? These are positive slopes and getting less positive. We don't know what rate they got less positive, but they're positive getting less positive than negative getting more negative, right? Then that would have changed this one. Because now these slopes are what? Negative and getting more negative, so that would start here and maybe come down. And then here they're still negative, but getting
Or less negative.
less negative. So they're still negative, but getting less negative, so it might come back like that, right? So if we'd have curved this one, then this, and then who's to say this one was straight? Maybe this one curved too. You know, it curved down, then curved up, right? Or was a parabola shape, okay? Because we really don't know at what rate it was doing this. All right, very good. There may be some other things, but that hits most of the big ideas. I think if you got through those, you can get through a lot of the rest of them then probably. But if you have, especially at 54, if you had, oh yes, sorry.
You can have any time to get this period.
Maybe right at the end.
I was hoping to have like that. He didn't figure anything out, but I said, let them do that.
trying to kiss up to you a little bit here. I said-
Thanks for pressing it. Yeah, right at the end. But then you got class 4.
Oh, you
I
are?
could sneak down.
If you snuck down during fourth, just give me a little bit of time to get them started.
Okay, I'll sneak down to 4th one. All right. Let's see. Everybody log in. Calculate. What happened with the calculators here now? Did everybody's restart kind of? I'll tell you what. Do this. Go to the. Oops. Everybody go to the home screen. Go to settings. Go to not that. Status, I think maybe. Settings. Status. And this version number. What's it say? If it says 1219 at the end, you're good. Does everybody say 1219 at the end? Then I think we got it. Nope. Everybody says 1219 at the end? Okay, then you should be good. Okay, so it must have worked. Okay? All right. So everybody get logged in. I got to begin the class. There you go. Now class cannot be started. Okay. Close the transfer tool. Close. All right. There we go. Okay, should be able to log in now. All right, and who's going to present today? Natalie. All right. So for this first part, I'm going to send, oh, whoops, maybe it won't be Natalie. Sorry, Natalie. If you really have your heart set on doing it, I can make sure you do. Okay. I want to send this document to everybody. Oh, whoops. No, oh shoot. No. Okay, I sent it to the wrong place. All right. I think we can move it. All right. Sam. Oh, you were presenter the other day. Weren't you? Weren't you just presenter? Riley. Riley hasn't been presenter. Are you good? Are you good with the calculator? Sure. All right. Okay. Go to My Documents. Everybody do this. Go to My Documents on the home screen. Go to the home screen. Go to the Press to Test menu, because I think that's where I just sent this file accidentally. Okay, there it is. Highlight that. Everybody, don't open it, but just highlight that file. Okay, in your Press to Test menu. Okay. Now go to the Doc menu. Right here, the Doc button, right above menu. And go to File. I'm kind of guessing right now. Okay, that's wrong. Go to Edit. Go hit the back left arrow. Go down to Edit. That's not right either. Okay, hit Escape. Okay, go to Menu. Maybe it's Menu. Go to Save As. Could have just resent it, probably would have been faster. Save As. Okay, right here. And save in. It says Save in Press to Test. We want to save that into our period 3. Go ahead and choose that. Wait, that's the only option that pulls down? Oh, wait, right here. Go up. Go, hit the little folder with the up arrow. Right here to the right. Click that. That'll move us up one level. Yeah, Hit escape. I think you're still in this. You're still in this, right? Hit escape. There you go. Now click on that folder with the info. There you go. And then you get the AP Calculus Period 3. Go ahead and double click on that. I think you have to go. There you go. And then, there you go. Now we're ready to save it. Now hit save. Whoop! Kind of save into the Zap. We don't want to do that. Why did it save into the Zap? Oh, because you hit that. Hit cancel. Hit cancel. Right down here. Hit escape. Escape will cancel. Escape will cancel. Okay. Now go to save. Go to menu again. Save as. Up folder. Choose this. Okay. One more time. Okay. Yeah. There you go. And now go to save. So it saves it with that name. Okay. Anyway, so we want to open that up. So double click on that. Yes, ma'am.
I don't have that.
You don't have that folder? Really? Well, that's weird. Well, here, let me try this. Let me try this. If that worked for you, here. Let's, let me do this one more time.
Something that you have to send to all the models.
Well, if I did just send it it might, I don't know. If I'd have just sent this to the right folder here in the first place, it'd have been easy. I think it'll create this folder now when I send it. Okay, I'm going to send it again. Now, it may ask you, do you want to rewrite it? Did you get it?
Yeah.
Okay, now go into your My Documents, and it should be, that folder should be there. I think it creates that folder when it's sent. And maybe when we restarted our operating system, it did that, I don't know. Okay, anyway. Well, okay, now Riley might not be the presenter. Sam Middleton is the presenter. Okay, so so go ahead and go to your documents. Yeah, I just closed that. Go to My Documents. Go into the AP Calculus. Open up that local linearity. Okay. All right. So section 1.5 is called zooming in. And what we're going to do, one of the things you had to do on today's homework was if you had a graph and you want to estimate the slope at this point, you would draw this tangent line, and there were some problems where you just kind of did that, right? Where you just sketched the tangent line, you kind of estimated the rise and the run. Something you'll have to do on our next quiz. Sometimes that's the best we can do. Is just kind of sketch that tangent line and then estimate the rise and the run, and there you go. Now, we want to be able to do better than that, obviously. So today we're going to talk about actually doing slope calculations. On your homework today, you'll do a fair amount of subtracting y's, subtracting x's, and doing a slope calculation, okay? So what we're going to do is we're going to talk about if we zoom in, we've already talked about this, right? We already talked about how the very first day we did this, right? If you want to do the slope at this one point, you can't do slope at one point, so let's do 2 points. Now, we'd like to have 2 points on the line. Unfortunately, we don't know 2 points on the line. We only know 1. But let's get 2 points on the curve. Now, aren't those 2 points on the curve really close to the 2 points on the line? They're almost the same thing. So if I pick 2 points on the curve that are really close and do a slope calculation, that'll be pretty close to give me the slope of that line. That's what we're going to do, zooming in. So go to the next page there, Sam, and everybody else can follow along. So control right arrow. Now we want to define this function. It's probably already done. This is just a calculator page. So arrow up. Just arrow up and grab that. There you go. Nope. Grab the define statement. There you go. Grab that right there. Hit enter. And hit enter again. Just to make sure it's done. Okay, so we've just defined f of x to be a 5th degree polynomial, a graph. Okay, go to the next page. And we should see a graph of that. Okay, there it is. Now in the yellow, we've zoomed in. So we're right there at about negative 1.3 on our x, and we've zoomed in. Now, what I want you to do is go here on these little triangles and click the bottom one and everybody do this, and we're going to zoom in. And we're just going to keep zooming in. Now, for a while, it goes kind of slow, and it seems like it's not really doing much, but it is eventually. So just keep doing it. Kind of looks like nothing's happening. Click too fast, sometimes then you get way behind and it kind of freezes up on you a little bit. But what's happening? It's getting straight, isn't it? And the idea, just keep going until it looks straight. Okay? And the idea there is that, just what I was just saying here, that if you zoom in close enough to on a point, on a curve, then it's going to basically look like a line. And if you were to draw that tangent line right there at that point, the line and the curve would essentially be the same thing. So the points on the curve would essentially be the points on the line. Remember, a tangent line touches the curve in how many points? Only one. So when we're looking at points on this curve, we're not really looking at points on the line, but they're really close to points on the line. Okay, so we're getting down to where it's, and that's as far as we can go, isn't it? And so it looks pretty much like it's straight. Okay, pretty close. So that's the idea. Now, if this was an actual graph where we could trace, we could hit trace, and we could trace at some points probably, and then we could do a slope calculation. Okay, open up your books. So that's all we need on that for right now. But Sam, I'm still going to use you some more here. Open up your books to page 48 and 49. 47 actually first. So on page 47. I told you, these guys have a decent sense of humor. I think it's more like my sense of humor. Yeah, we're zooming in, so we're literally taking a closer look at these slopes, okay? So right here on your book, you see here on page 47, we've got a parabola, we've got a couple of tangent lines. We're going to zoom in here on this negative 1.5, this one on the left. We're going to look at that, okay? So if you turn over to the next page, all right, in the middle of the page, you see a table of values. What they've done is they've went in, and on the parabola x squared, they've actually picked out some points, okay, some parabolic points. So what we're going to do then is look at, we're going to actually then calculate some of those. So give me some of those. So if I wanted to do f prime of 1.5, negative 1.5, if I want to do that slope on that graph, and this is a bad example, it was this right here, so it looked like it was about right here. If I want to do that slope right there, okay, and get an approximate value, would it make sense to take a point on each side? Right? We did that day one, so you guys have seen this before, right? We've talked about this before. So what would be a point on the left side? Well, on the left side, or let's do the right side first. So the right side would be f of negative 1.4. Would that be correct? Would that be that'd be the right side of negative 1.5, right? And the left side would be negative 1.6. And then we would subtract those. Right? So we would just go on each side. All right? And so now, since they gave those values to us in a table, some of your homework is going to be like this. You're going to get a table of values. And it's going to be really simple. I mean, some of them are very simple. They're going to say, find the slope, estimate the slope at this point. Well, just take 2 points, one on each side, and subtract them. So what's f of negative 1.4 in that table? 1.96. And what's f of negative 1.6? 2.56. And here you get, I don't know, 1.2. Tell me what you get. Go ahead and just, on your calculator, you can just hit the scratch pad now. If you're still in that document, just hit the scratch pad. Get your calculator straight up. And then just do that calculation. Now, I'm going to want to see this on your paper today. When you calculate these, I want you to write down, because on the quiz, when we do this, I want to see the slope calculation written out. Now, if you want to just do this first one I have with the f of, if you want to do that, that's fine. Or if you just want to have this one, you wouldn't have to have both. Okay, what do you get? -3. Now, it won't always come out that nice, but in this one it does, okay? So does that seem reasonable that that slope would be about -2? Sure. So the work we did ahead of time last week hopefully really helps us, or 2 weeks ago, helps us, in doing this, right? This idea of zooming, pick 2 points really close, helps us to get an approximation of that. So last chapter, or yesterday's section, we were just kind of sketching tangent lines, just kind of estimating what those slopes were. Now we're literally taking a closer look and actually being a little more exact, and we're picking some values and finding those. Okay, last thing I would like to do, and I really think this is cool. So Sam, you're gonna do this for us. Everybody else can do this as well. What I want you to do is go under Doc to File, New. If you're on the home screen, you just go to New Document. Now it's going to ask you if you want to save this. I'd say no, not important to save that. Okay, I want you to go to New Document. Okay, and then just get to this screen and don't do anything. Okay, once you get here. Now if you're on the home screen, just go to New Document, and it's going to ask you, this will come up. If you're already in a document, go to File, Doc, File, New. Okay. Now what we're going to add first is we're going to add a list and spreadsheet page. So in our new document. So go down to number 4, add list and spreadsheet. All right, now this is just a spreadsheet like an Excel spreadsheet. What we're going to do is we're going to calculate the slopes of the sine graph. So here's a sine graph. We're going to go from 0 to 2 pi, and we're going to go in pi-8 increments. And we're going to calculate the slope. So right here, 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 we're going to calculate that slope. Now, in the old days, 2 years ago, we would divide up into groups, and you would get on your calculator, you'd zoom in, zoom in, zoom in, zoom in until it looks straight, you trace, you find 2 points, you do a slope calculation. Okay, we got these calculators, we got a nifty little spreadsheet out for us, so we're going to let it do most of that calculating. Okay, now I did think there was some value in doing that, but you're going to get some of that in your homework. Understand that we're going to zoom in, and we're just going to basically see what these slopes are at all these different points. And then we're going to plot them, right? Isn't that what we've been talking about? The f prime graph is the slopes of the f graph. So I'm going to calculate all these slopes, and then I'm going to plot them and see what the graph of the slopes of the sine graph looks like. Okay, so we're going to need this first column. Let's call this x. Call this, go arrow up here to A. If you're going to follow with me now, if you get behind, I probably don't have time. Well, we probably do, but I may not slow down. So if you get lost, not a big deal. It's more of a visual thing. I mean, that you see it as much as do it, but it's kind of good to go through. So we're going to label this column X. So it's just like a spreadsheet. Okay, and then arrow on down here. Now I think, let's see. Yeah. Okay, I want to put in this first column, I want to put a 0. We want to go from 0 to 2 pi, and we want to add pi-8 each time. Now, there's probably a faster way to do this, but this will work. So put a 0 and hit enter. Okay, now, in this column, all right, everybody with us so far? So we're down here on A1, we put a 0. Okay, in this column, we want to put a formula. Now, anybody from you guys familiar? You had to do some spreadsheet work, right? Excel spreadsheet. What do I have to do first to put in I have to put an equal sign. So put an equal sign. And what I want to do is I want to take the previous cell and I want to add pi-8. So we just go, what's our previous cell? A1. So just hit A1, and it doesn't even have to be capital A, that's fine, plus, and then we're going to go pi divided by 8. Okay? Pi over 8. And hit enter. Now arrow back up to that, and we want to fill that all the way down. So where that is under menu. So everybody get your highlight pi-8s, go to menu, go to data, and go to fill. And now it highlights that column, and now we're just going to down arrow, and let's see. We need 16 pi-8s, that'd be 2 pi, right? And when you count 0, wouldn't that be column 17 probably then? I think row 17 is where we need to go. So go all the way down to 17. Because we need 16 pi-8s plus the 0. So hit enter. Cool. Got it. Okay? All right. So now let's arrow back up to the top again. Oh, now I forgot. I want this to come out decimals. I don't think it hitting the approximate button will work. We could try it. Okay, go to the next one. Okay, so now in this column, let's label this column Y. Okay, or yeah, just call it Y. It doesn't matter what we call it right now. But this is going to be our outputs now. So this is going to be the sine outputs. This is going to be the sine outputs. Okay, so we go to and in here, what do we want to put for our formula? Sine of A1. We want this column to be the sine of the first column. So we want to hit equals. Yeah, when you hit enter, let's hit control enter when we do it. So go equals, and then sine A1. Yeah, I don't think you could do the approximate at the beginning. I think it needed equal. Now hit control enter. Let me see what that does. Oh, well, we can't tell because it can't. But we'll be able to tell here in a second. Okay, so now arrow up to that, and we want to, so see it says sine A1 down here. Now we want to go to our data, go to our menu and data and fill. And then we want to arrow down to 17 again. Hit enter. Yeah, hit control it. Hit control it. Nothing happened. Okay, hit enter. Yeah, hit enter. Yeah. Yeah, see, okay. So here's how we're going to have to do it. So go to the document. Go to the doc menu. Go to the doc menu. We're going to go to settings and status. We're going to go to document settings. I think that'll just do it for this document. We're going to go to the calculation mode, and we're going to change auto to approximate. Because I'd rather see decimals in it. And then hit OK. I think that'll only change that. Now, if that starts changing your calculator stuff, then you'll know where to go with it. Okay, there we go. Now, it's giving us decimals in that other column too, but that's okay. Now, arrow back up to the beginning. Now, this makes sense. Okay, look at our values. 0, 0.3, 0.7, 0.9, then all the way up to 1. Remember that was pi half? And that's a sine graph. Look what it does, right? Now, this part is so cool. I want you to go to document. Once you go to the document, right now. Okay, we'll wait, Riley. So you got it? Okay. So now we got those two columns filled in, right? Go to document, go to insert. Go to the doc button, go to insert, and we want to insert a data and statistics page. Now, these are all those random points that we just got done doing. Okay, but see where down here it says click to add variable, click to add variable? Okay? Down, what this is going to make is a graph, and it does it all for us, right? It sets the window, does everything. Click to add variable. What variable, which of our X or Y do we want down here? X. Which one do we want here? Y. Very good. So you go down here, arrow down here until it puts a box around that, and then click, and then it brings up your variables you have in that other spreadsheet. Choose the X. Okay, oh wait, it gets better. Now arrow over here until that box pops up along the Y-axis. Click, do the Y. Isn't that cool? And it sets the window, does everything. So it just plotted those points for us. Cool little sine graph, okay, which is what we expect. You ain't seen nothing yet. All right, go back to page 1. Go back to page 1. All right, now, no getting ahead, because if you ooh and ah, ahead of time, that'll ruin it. Okay, so go over here to the C column, get up here, and let's just label that Z. Whatever, doesn't matter. Okay, we just need to know that's a column we're interested in. Okay, now, in this column, we want the slopes of these points. So tell me how, and hint, okay, tell me how we could get the slopes at each of these points. Pick 2 points really close and do a slope formula. So wouldn't it be, now let's all right, he's missing something really cool. That's Spencer, he knows. All right, look. Let's just call that point. Let's just call that point X. One of those points, right? we need a point just to the left of it and a point just to the right of it, right? And we need the y values, of course, to be sine, right? So let's go like 0.001. So let's say that was x. So don't type anything in yet, but wouldn't it be something like this? Wouldn't this be a point just to the right of point x? And then just to the left would be sine of, wouldn't that give me my y values, one just to the right, one just to the left? And what would go in x? Well, that'd be that first column, right? The pi 8s and the pi halves, right? Those numbers. And then what would be the bottom? Well, wouldn't it be, it'd be this point minus this point. But what would happen when you distribute the negative through there? The x's would drop out, and this would turn positive. Well, now wait a minute, does that make sense? If I go 0.001 this way and 0.001 this way, what's my run then? 0.002, right? I mean, it's rise over run, right? It's rise over run. So 0.001 this way, 0.001 this way, subtract those, that should be 0.02. So that'll make two, so we'll just do that. Okay, so back to our thing. So in our formula, right here, we want what? Equals, do it, control, divide, yep, to get you a fraction would be nice. So up on the top, we're going to want sine of, left parenthesis, well, we'll be careful, not an x though. We don't want x there. What do we want? A1, right? We want sine of whatever x value we're at. And when we fill down, it'll do all these, all at once, right? Isn't that right? So we want just to the right of 0, 0.01. Okay, then right arrow outside the parentheses, minus, and then we want sine of A1 minus 0.001, right? Isn't that going to do it? Because A1 is our x value. A1 is our x value. And now on the bottom, what do we got? 0.002. Correct? Now, let's just hit enter on this first one. And before we fill down. Okay, now look at that. Arrow back up there. So 1. Is that reasonable? Is that reasonable on the sine graph? The slope here is 1? It's reasonable. Yeah, makes sense. Okay, let's fill down. So go ahead and highlight that. Go to your menu. Go to your data. Okay, now arrow back up. Now, hey, don't get ahead. I know some of you guys know where we're going. But I want you to see a couple things. What are the slopes doing? What do the slopes seem to be doing? They're getting less, right? Oh, what's the sign? What are the slopes doing? They're positive but getting leveling out. And look at some of these values. They look kind of familiar. 3, 8, 2, 9, 7. Oh, gee. Where are we going next now? Let's go to that next page. Go to that data page. Okay? Now, what do we want to graph down here on x? Whoa, 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 whoa. What do we want down here? Still want x. X never changes. X never changes. What do we want to graph here? We want to graph z this time. We want to graph the slopes. Won't this be the f prime graph? We want to plot the slopes. Oh, do it. What is it? It's cosine. Are you kidding me? The slopes of the sine graph make the cosine graph? Absolutely. You just learned your first derivative formula. F prime, if f of x is sine x, uh-oh, whoever's getting recorded is not seeing this. Oh, then, they should have been here. If f of x equals sine x, f prime is cosine x. The cosine y values are the slopes of the sine graph. But doesn't it kind of make sense? We just said, what are the slopes? They're positive and getting less positive. What's cosine graph do? It starts at 1 and goes down. And at pi halves, sine has a 0 slope, 0 output. And then sine graph starts going down, so negative. Absolutely, and they're exact. You saw in that spreadsheet, they're exactly those values. They're those same type of values. I just always think that's really cool. I don't know, I'm weird. Anyway, it is cool, isn't it? I mean, you know, and especially cool when what we used to do is we had to plot them and then we would get it and then you can't see it. But this just kind of magically, it's pretty awesome. So, you missed like 3 minutes of.
Ah,
All right. So that's right. That's it for tomorrow. Now, so a big part of your homework, it's the 1.5 homework question. A big part of your homework are doing these slope calculations right here. Okay, a big part of your homework, there's tables of values. Estimate the slope at 1. Well, you pick, if it's a table, you pick a point to the left of 1, you pick a point to the right of 1, you do the slope calculation. If it's a graph, you might zoom in. They might have you literally zoom in on your calculator until it looks straight. Okay, and then trace. Just pick a point on the left, point on the right, write them down, and do the slope calculation. Okay, so there'll be a lot of that. But the bigger idea that we take forward then to the rest of the section is this idea that, like we did here with the sine and cosine thing, that when you figure out the slopes of the f graph, you plot those as y values, that's the f prime graph. And then we're going to really talk about the connections between the f graph and the f prime graph and what that tells us and all that stuff. So 1.5 homework for tomorrow. Hey, that's cool. What'd you just do there?
Put the Y in.
Oh, you put the y in there. Hey! But it's the other way around. What's a unit circle? Cosine is the x, and sine is the y. So cosine was the z, right? So put z here. Technically, to be technically the unit circle. That's cool that you just recognize that, though. Put z here and put y up here, right? Y with the sine values. Z is the cosine value. So if you make cosine the x and sine the y, you get the unit circle. That might even be cooler than.
That's well, I
Oh yes.
did that.
Okay.
Oh, yeah, because the backside.
What's that one?
It's just the X. and
If
Y.
you interchange the x and y, what's that called?
Not a function.
It's not a function, but isn't that the inverse sign? That's an inverse function. You interchange x and y. So go back to that graph. Go back to that document. Just go to current. So what was this, sine? We have sine down here and x up here. That's the inverse sign. Inverse sign.
So down here, just be inverse cosine.
Z down here would be inverse cosine. There's the inverse cosine. Yeah. And look where the peak is, right here about pi, 3.14. Yeah. 3.14. Negative 1 to 1 down here. Sine and cosine values for negative 1 to 1. Awesome.
I was on